Okay, so we have we got a lot of information here, but what we're stuck with so far is that we're stuck with the atom with protons, and electrons should collapse in on the protons, and we still can't figure out why why they don't collapse um, and what's going on, and so we're going to try to put that all together here, and the guy that that sort of puts this all together, um, and he doesn't get as much play as as he should. It's a guy named Niels Bohr, and he's a man from Denmark. Um, he's a contemporary of Einstein. He actually worked with. He was a student. He worked with Ernest Rutherford. So after Rutherford came up with um, his idea of an atom, which has a proton and electrons around it, uh, Bohr started working with Rutherford and wanted to see if he could figure out at, more about that and if it could be more precise. And all kinds of people came up with all kinds of different ideas of what was going on. Some people said there was electrons inside the atoms and the protons were whirling about, and some people were saying there was thousands of electrons flying around in all kinds of ways, and there was all kinds of incredible mathematics that were proposed to come up with the structure of atoms, and a lot of them kind of worked, but um, most of them weren't able to explain it. Weren't able to explain, especially what was going on, why they didn't collapse. Okay, and Niels Bohr is about 30 some years old. 19, and what he does is that Rutherford, you kind of can think of as came out of a planetary model. What that means is that you have protons in the middle and the electrons are orbiting the protons, and he wanted, and so Bohr did uh, some assumptions and statements, and he built from that. It's sort of like the philosophers of the ancient times. He came up with some basic assumptions and said, let's work with them. He said electrons can exist only in specific orbits about the nucleus. That means they just couldn't be so. Uh, in Rutherford's model, the electrons could be moving any willy nilly all around the place. So what Rutherford says is they gotta kind of be like the planets going around the sun, right? And the odd thing about it is that when they go around, they don't give off any energy. Okay, which is counterintuitive because if the electrons are going around, they should be getting off energy. But but Bohr says when they are in these orbits, they can go around without giving off energy. And he said, don't worry about it. Let's just assume that. Okay. And he tried to say that things are gonna. He said he's gonna try to have everything fit according to the physics that were known. And the other thing that he came up with is that for electron to move from one orbit to another, it had to be given an exact amount of energy, and that energy was Planck's formula. Just like in the photoelectric effect, if you knock an electron out and it's got having specific energy, well, Bohr said for an electron to be knocked from one orbit to another orbit, it had to be given a very specific energy. Okay, so here you go. So you have your three assumptions. Okay, the third one was the most controversial because it's saying you jump from one to another. Just like Planck's bin idea was controversial because he said that going from one bin to another, you had to jump from one bin to another. You just didn't flow, you jumped. Right. And so what Bohr did is he looked at the spectrum and he looked at this formula here, okay, from Rydberg's equation and so forth. And he actually tied this guy here with E equals H nu. Okay, and that's what we'll want to look at here. Now, just give you a little hint here. So, if you want to knock an electron from point from 2 to 3, you have to add a very specific amount of energy, Bohr said, and it has to be this energy here. Well, this guy here is the inverse of here, compared using the speed of light. And so what he did was he combined Planck's constant with this equation here to come up to help to explain this. All right, so we're going to put it together. So we have speed of light, and we have the Balmer equation using Rydberg's constant. So we're going to combine those two. So we can see that Balmer's equation has 1 over lambda equals this. So what we're going to do is rearrange this equation. So it's the frequency is equal to c times 1 over lambda. So we have that. We have the frequency is equal to this equation with this equation, right here. And then what you can do is combine this equation with this equation by substituting the frequency by this, and so we have this here. And H is Planck's constant, C is speed of light, and Rydberg constant. And you don't have to memorize this; you'll be given it. And this too can be changed to N1 or N, so we can call it N1, and we call this N2. Right. Okay. So this is one way of representing what's going on. So, and we're going to do a problem nexus. So we get this equation right here. And it predicts the energy levels and also the transitions from one energy to a level, to a next level. So if I want to find out the energy that's released, that's going from energy 1 to energy 2. So if I have an electron here, and I want to move it out to this energy here, and remember it's very specific. It's not, you just can't go from here to here, but it's very specific. So if it goes from N1, we'll call this to N2, there has to be a certain amount of energy added, okay? And that energy will be a positive value. Now, we could go the other way as well. You go, so this guy here is lower energy and this guy's higher energy. We'll talk about that in next couple of slides. But so if you go the other way, you go from N2 to N1, it loses energy because it goes to lower energy, and that, in that case, it would be an exothermic reaction, negative. Okay, so let's do a couple problems. All right, so let's use the formula to figure out the energy between how much energy it requires to move from one energy level to another using what Bohr came up with his formula here. So if you look at this is a constant, Planck's constant, and the speed of light and Rydberg are all constants. And what we're going to do is just do the calculation for this in one trial, and then what we'll do is, and then we'll just use the number we get from this and use it for other experiments. Also, what we want to do is that this doesn't have to be a 2. This could be just some energy level going to some other energy level. All right, so let's figure out these numbers here. And so here's Planck's constant, here's speed of light, and here's Rydberg's constant. Now, if you do go ahead and do the math, and I like to do a mode fashion. So what I like to do is I like to multiply it 6.63 by 3, and then 1.1, and I get a value of I had a value of 21.9. Okay, and then I just added the exponents. Okay, minus 34 plus 8 plus 7 ended up with being to the 19th. Is that right? So 34 subtract 8 is 26. 19. Okay, so 19. So I originally had this, all right, and then to get to scientific notation, I change this to 2.1 times 10 to the first, and then add the 10 to the minus 19th, and I get this. All right, and so that's what this first part is. Okay, now so then I just have to figure out the jumping from one energy to the next. So let's say I go from energy level 1. So here's sort of your diagram. It is definitely not an exact one because we're looking at its orbits, but this is the way Bohr originally thought it. So if you go from energy level 1 to energy level 3, okay, what you need to do is you need to add energy. Okay, so there's going to be a positive value here. This energy is going to be absorbed. That energy is going to be absorbed from a light wave that has a specific wavelength, and we could figure that out just as well. Okay, so what you can do is you can just figure out solve, use the equation to solve for lambda instead of energy. So there'll be some problems that you'll have to do that. So I want to figure out the energy. So I take the value that I got up here, 2.1 times 10 to the minus 18th. That should be all right. And then energy level, I go from energy level 1 to energy level 3. And so that's simple math. 1 subtract 1 over 9, and you come up with plus 1.95 times 10 to the minus 18th joules to go from energy level 1 to energy level 3. Okay, then we'll do another one from energy level 1 to energy level 2. Again, same thing. You use the same number here, and then you come up with this. Okay. Okay, so let's go a little further with the one problems here. So what we want to do is find what is the wavelength and frequency of the light that is required to move the electron from energy level 1 to energy level 3 from the last problem. So again, you have your 3 orbits here, and then what you do is you have your electron and some wavelength, specific wavelength, very, very specific wavelength has to come in, hit it, and when it hits it, it'll knock it out to energy level 3. Okay, so let's find out what that energy is. Well, we know the energy from the last problem. And then what we simply do is take Planck's constant, okay, because it has energy and it has frequency in it. And that's the kind of thing, if you take physics, you're going to be doing a lot of this. Is that you always have to find the right formula to work problems. And so, you'll be given a battery of formulas and you'll have to figure out problems. we won't do a whole lot of that in this class. This is about the only place you'll see that. So here, we're doing that here. So here's Planck's equation. And then we rearrange the equation for the frequency. All right. Okay. And then you simply solve for the frequency. So that's going to be the energy divided by Planck's constant, and the units work out. Joules cancel out, and you end up with per second. 2.91 times 10 to the 15th cycles per second. So that means it's not just this number over this. It's how many times the wavelength goes up and down. Now the other thing about this is that, let's say the last problem you had a negative value here. You have to ignore the negative because frequency cannot be a negative number. So if that would have been a negative number where the energy has been released, you just have to ignore the negative number because it can't have a negative frequency. All right, to figure out the wavelength, so this wave not only has frequency, okay, it also has a wavelength, and you do that, you just use the speed of light equation. The speed of light is equal to frequency times wavelength. Solve for wavelength, and then plug everything in, and you get 3.0 times 10 to the 8th minor meters per second divided by 2.91 times 10 to the 15th. That's this value up here. And again, your units cancel out, the seconds cancel out, and end up with meters. 1.03 times 10 to the 7th meters. Okay, so that's the kind of problem that you'll have to do for this section here. All right, now so Bohr has this model, and this model says is that you have now the electrons just aren't randomly moving around the protons. They fall into orbits, and when they do fall into orbits, somehow that when they in there, they may be moving, but they don't. When they in those orbits, it's like a trench, and they can't get out, and they don't collapse in on the proton. And he said, and so he said you have your protons, and then you have your levels: energy level 1, energy level orbit 2, 3, 4, and so forth. And that's what we call our beginning of our quantum numbers. And this is our first quantum number, is the energy level. So electrons are found in different energy levels: 1, 2, 3, 4, 5, 6, 7, no halves or thirds, whatever. So it's always a very specific quantity: 1, 2 quantities, 3 quantities, 4 quantities. And we're not going to call them orbits anymore. They're going to be either called energy levels or shells, because this will get confusing. In fact, the whole idea of a planetary model will be confusing. All right. Some of the people worked with Bohr. They started looking at empirical data. One of the guys was a fellow named Arnold Sommerfeld, German man, and he looked at the empirical data, and he said the way to explain some empirical data is to explain, it says that the orbits don't always have to be circular, but they could be elliptic as well. And depending on the elliptic, if it's like a full circle, it have one kind of value. If it's more squished out, have another value. And just so this was given the second quantum number called L. And we'll see that this relates to something called subshells, and we'll get into that. And it also has quantized values. So circle has a value. He said so a circle would have score of 1, 0. The more elliptoid will have 2, I mean 1, 2, and 3. Instead of starting with 1, it started with 0. So you have your first quantum number starting from 1 and moving on. The second one started from 0 and moved on to 1, 2, 3, 4, 5, and 6. Now, Summerfield also looked it up, further dated, is that not only could they be different shapes, but they could be tilted differently. So you may have a shape of 3, but it may be tilted. And so he gave that another number called M. And so it could be tilted this way or tilted this way. And so he said if it was tilted just straight across, we'll see this, but possibly like if you had this guy here, it'd be tilted here would be a 0. If it's tilted this way, it'd be +1. Be tilted this way, it'd be -1. And we'll get more into this, but I just want to let you know that right now electrons can be defined more than just their energy level. They can be defined by the shape of that energy level and how it's tilted. And we're going to change that because this is the old model. Okay, the last quantum number is given ML, and it was determined by this gangster dude, Wolfgang Paulin. No, he wasn't a gangster, but he was really, really, really smart. He was considered like the smartest guy outside of Einstein, or maybe even smarter. What he did was very simple, but it changed all of how we look at all of this. And what we're going to do is make this very, very simple. He said that whenever you have electrons have spins, okay, they can go, and the spins can be, they go clockwise or they can go counterclockwise. Instead of saying counterclockwise or counterclockwise, they would say it goes up or down. And he said that an electron could be either up or down. And then when it is in one of these shapes, so if it's in a elliptical shape, there'll be another electron, there'll be another electron that can also be in that same shape, but it has to have the opposite spin. Okay, and he designated these spins as being halves. So one would have, like, a down spin would be -1/2, the up spin would be +1/2. So in each one of these shapes, okay, there could be 2 electrons, and one of them could be only 1, but there also be 2, but it can't be any more than 2, and the 2 have got to be opposite. Okay, and we're going to see how this all comes together in the big picture. All right, just here's kind of a funny little thing is that it's this called Pollys exclusion principle, that you can't have you can only have 2 electrons in an electron in an orbit, and they got to be opposite pairs. So somebody asked this question in test, and there should be no pairs allowed, and the person wrote down no parrots allowed. Right, kind of funny, but maybe not. All right, okay, so Bohr's model was not proved. It was more conceptual than anything. It did not have substance to it, and so it had to match and be had to be described mathematically. And so this is where the next step. And so in the early 1920s, this really went full bore. Okay, so what we're going to do is look at what you could be called the new quantum model. What Bohr came up with was considered the old quantum model. We're going to kind of combine the two in the long run, but let's look at the new quantum model. All right, a fellow named Werner Heisenberg. He was a young man, this is 1925 or so, and he was about 25 years old. So he was born. He was like 5 years old when Einstein came up with all his great stuff. He came up with he did some pretty amazing stuff actually. He tried to figure out the math of the electrons, and what he did is he went off onto an island off of Germany, and he really had really bad hay fever, and he wanted somewhere where he could just concentrate without getting sick all the time. So he went out to this island and lived in a little hut, a little house, and just walked a lot, and wrote letters to Bohr, and did a lot of math. And when he came back, he came back with the mathematical formula that made it all work. The problem is that it was really kind of bulky and didn't make sense. Okay, it worked. What I mean by didn't make sense, it didn't make sense in terms of reality. We couldn't apply it. Couldn't say, oh, electron jumps out and it falls here, but the numbers all worked. Okay, and we're going to see that his model was actually verified, and it does work compared to other people's ideas as well. But one of the big things that he came up with when he did this is that he came up with something called the Heisenberg uncertainty principle. And don't worry about the formula, but what it says is that the more likely that you know, more accurately you know the position of an electron, less you know about its momentum or speed or energy. So if I know where electron is, I don't know how fast it's going. That's kind of the idea. So it'd be like if you're driving down, if you're on the highway and the police officer has got his radar and he takes your speed, okay? And he comes up with the speed of 80 miles an hour, right? What this says is that as soon as he takes your speed, he knows your speed, but he no longer knows where you are. And I just don't mean like going real far or down the road, but you could actually be 100 miles away, 1,000,000 miles away, whatever. The more you know about speed, the less you know about its position. And the other way is true. The more you know about where something is, so like if you look up at the sky and see the moon, according to this, as soon as you look at the moon, you don't know its speed anymore, and actually that means it could change the whole speed of the moon, where it is, okay? So in terms of our view of the world, this doesn't make sense, but it works for atoms. So basically what this says is that you never really know where an electron is. All you can do is guess where it's going to be with certain kind of probability. And that's what's going to happen next. Try to figure that out. All right, now a giant stroke of genius happened about the same time with this guy over here. He's real happy, and his name is Broglie. I think his name's Ernest, but and he's a French guy, and he's born into royalty, and he gets bored. He's supposed to be he goes in the army for a year, and then he gets bored, and he decides he wants to do physics, and so he comes up with the idea. He's like 25 or so. He says, well, if light can be a wave or a particle, so a wave can, why can't matter, like electron is is supposed to be matter, solid. Why can't it be a wave? And so he came up with that equation. And so he said is that the wavelength of matter is related to its mass. Now, it seems preposterous to think that solid things, like a piece of wood, would be a wave. It seems like it's a piece of particle. But de Broglie came up with this, and they kind of scoffed at it, but it actually turned out to be proved a couple years later, and Einstein actually stood up for de Broglie, and this, along with Heisenberg's the uncertainty principle, led to the big equation that we all sort of look to now. So what de Broglie said basically is this: is that you can have so energy levels are going to be in terms of 1, 2, 3, 4, 5, no halves. Okay, so he said is that they behave like stationary waves, where they have exact a number of our waves. So this guy has 1, 2, 3, 4 waves. It doesn't have a 4.5 waves. So this seemed to fit. So this idea of a wave seemed to fit the idea, the quantum effect of going from 1, 2, 3, 4, 5. All right. And so you could think as energy level 1 would be a circle. Energy level 2 would be like a wave that has 2 crests. Energy level 3 would have 3 crests. Energy level 4 would have 4 crests, and so forth. So there's no, so it goes up, so it does go up by 1, 2, 3, 4, 5, 6, and so forth. So it does seem to fit the idea of quantize. All right. Okay. So this fella here, Erwin Schrödinger, decided he's going to figure it out. And he's going to say he wants to figure out in terms of the wave with de Broglie. And so he left for the mountains. And actually, he went up there with his girlfriends. And he had more than one. And so he was an interesting guy about that. He looks happy. And maybe because of his hanging out with his mistress. But why he's not messing around with his girlfriends, he comes up with the equation. This is all calculus stuff. And it's a crazy formula. And I'm not even going to try to explain it because I'm not sure about all of it. But this thing right here is the key. And this thing here is called the wave function. And so what it is, has this equation, says is that the electrons have a wave function. But you really don't know what the heck that means. Does it tell me where the electron is? Does it tell me how it behaves or whatever? All right. It can tell me the energy, but it doesn't tell me much else. Okay, one of the people that looked at it decided, it said that it just doesn't make sense, but it works. So how can it make sense? So this guy named Max Born said, you know what this is like, so if you guys know anything about statistics, you have variance, and then you have standard deviation. Okay, the square root of variance is standard deviation. And that's kind of what he did here. He said that the wave function is basically like the variance, and the square root of, okay, no, sorry, I had the other way around. The wave function is like standard deviation, and when you square it, it actually tells me the probability of finding the electron. So the wave function really is not, it doesn't tell you anything, but when you square it, it tells you where you're going to find the possible regions you're going to find the electrons. And what this did, Born's idea, is it made sense of Schrodinger's equation. So whenever we do Schrodinger's equation, we solve it if we can, okay, and then we square it. And when we square it, that tells us where the electrons will be, and we're going to see uh, what these results of these equations will look like. Okay, so finally, somebody that just took it to the next level is this guy named Paul Dirac. He actually wasn't from the United States. He was from England. He put together and he came up with this equation. Good luck with that. I don't know how to work it, but if you take higher level physics, you can work on it. Okay, so up to this point, what we've done is basically come up what we need to find the electrons in atoms and their structure. And what we have is, we started with Bohr's model, and Bohr's model is, like I said, it's conceptual, but it didn't fit the bill in terms of the mathematics. And so Schrodinger, Heisenberg, and Dirac, and etc. all came up with a formula that works. What we're going to do is let's sort of combine the two. We're not going to do any math. We're going to sort of rely a little bit heavy on Bohr's idea of orbitals and energy levels, but we're going to kind of reset it in terms of Schrodinger's equation. So you won't have to know the formulas, the Schrodinger's equation, etc. I mean, some of you may want to do that in your future, and good luck to you. Then you come back and tell me all about it. And but so what we have now is we have energy levels, which Bohr found. Well, first of all, we have Rutherford's model with the electrons, negative electrons, swirling about the protons, and the protons are in the middle, and the atom is mostly empty space. Now that created that problem is that you can't have electrons just flying around without losing energy, and so what Bohr came up with, based on spectral analysis of hydrogen gas, he came up with the idea that the electrons are situated in orbits going around the proton, and these orbits are stable, and that means is for some reason electrons can go around them without losing energy. And he said that to move from one energy level to the next energy level, you need a specific amount of energy. You just can't add any amount of energy. An electron will move to another energy level. And this is the idea of quantum, based on Planck's formula. Discovery. So Planck's discoveries plays heavily on all of this. So it's pretty amazing that Max Planck doesn't get as much play as he should in our world of science. But if you really get into this, you'll find that the Planck's equation and number is a really, really important concept. And then we through the idea of de Broglie, he said that the electrons can not only be particles, that they can be waves. And so now, and then what Schrodinger did is he came up with the formula to tie that all together. But it really didn't really say much, because it came up with this thing called electron can have a wave function, and really people didn't really know what that meant. And what it came down to, Bohr said that this wave function, if you square it, what it does is it tells you the probability of where the electron is found. And that's the key thing, also based on Heisenberg's uncertainty principle, is we'll never be able to know where an electron is. We'll only be able to predict where it is. But we can predict it with a pretty good amount of probability. And so what we're going to end up doing is producing a model that has energy levels. And then the energy levels will be these probability, the probability of finding the electron somewhere in that energy level. And then we're going to build up from there. So there will be different components of where electrons are found in the atom. The most basic position will be energy levels, and then we're going to look more specifically at where they are found in the energy levels, and those will be called orbitals. And you'll see that in the next PowerPoint, where we'll develop that with this material here in a more conceptual way.